All right, concentration, the amount of solute per quantity of solvent. So solute per solvent. Concentration can be measured in several different ways. One of them is mass per volume percent. So we can say, like, you can just say M over V percent, or we can say mass to mass percent, which is M over M percent, or volume to volume percent. This isn't really complicated stuff. This is always comparing a solute to a total solution in every situation. It just depends what information you're given in the question. And it depends if you're given, you'll know which one you have to use by if you're given the masses or the volumes in general, right? So it'll be really clear which strategy you have to use, but each of them follow what you would expect for how a percent equation would work. Okay, so the first one is going to be mass per volume percent, and that's going to be the mass of the solute in grams. So if it's not in grams, you got to convert it to grams, over the volume of solution in milliliters. And again, if that's not in milliliters, you got to convert it to milliliters. Solubility is always measured in mass of solute over mass of solvent. Don't like the black. It's too boring. So we'll give this a try with a couple of examples here. First one, if we've got 16 grams, that's not the highlighter. Scratch that. If you've got 16 grams of sodium chloride dissolved in 500 mils water, what is that's basically asking you, what is the mass to volume percent? So the setup that you can use, you're going to make sure that you write down the information that you've actually got. So we're going to say that our mass of the solute is 16 grams, NaCl being the solute. I'm going to make this bigger so I've got a bit more space. That really helps. And then the volume of the solution is, what's the volume? 500 mils. Ooh, 500 milliliters. There we go. And we want our volume of solution to be in milliliters, so that's good. So then you can say mass to volume percent. This is complicated stuff, isn't it? It's going to be the mass over the volume times 100%. Someone calculate that out for me, please. 3.2%? Thank you. Oops. Should I put I'm going to put the unit in. I think the unit's still going to matter because we want to show. Should I put the percent though? Yeah. I feel like you need to, just because some of them are mass to mass, and those ones will cancel out, right? The gram to gram will cancel out, or volume to volume, those will cancel out. So I think in this situation, because you've got mass to volume, or as long as you've got that part written there, I think that's probably okay to leave grams per mil out. Does that sound reasonable? I feel like that's fair. So far, so good? Yeah? La la la. Let's go to this cleaning solution. So this time, what are we given? Bless you. We're given the mass to volume percent. It's 2.7%. What's our volume? $1.5 liters. Whoa. What should we do about that? I'm going to have to convert that, right? Convert it into milliliters. We want to know mass. Okay, well, I know that mass per volume percent, the nice thing about it, it's kind of got the equation in it. It's going to be mass over volume times 100%. Get in there. There you go. What do I want? I want mass by itself. So I'm going to say mass is going to equal mass per volume percent times volume. Is it okay if I just write 2.7%? Like if I do that, you know that you have to do something with that on your calculator. You either have to use the percent button or you've got to divide 2.7 by 100. Is it okay if I just do that? Times 1,500 milliliters. Yeah, so here is where that unit actually might matter, right? So I'll write it down for you. Don't have to show all of these steps every time because these are going to become quick and easy calculations for you. But that's essentially 0.027, and that was in grams per milliliter percent times 1,500 mils. So that's how your milliliters cancel out. What do we get? 40.5? Sweet. Jillian?
Where'd you get the 0.027?
So I just did that step, this one here, 0.27%. That's what, if you have a percent button on your calculator, if you hit 2.7 and then hit the percent button, it will convert this into decimal form. Okay? So that's what that's doing. If you don't have a percent button on your calculator, you're going to go 2.7 divided by 100, and that will give you that number there.
Okay.
Okay? Does that make sense?
Yeah, thanks.
No problem. How are we doing so far? Is this okay? We're going to look at mass to mass percent. So it's the same thing, except you've got mass over mass instead of mass over volume. And of course, the masses, they need to be in grams. So in this situation here, we're given, oh, sorry, Alina? Yeah, as long as they're both the same in this situation, they matter. The time that it doesn't matter. That's what I want to say, right? As long as they're both, like, because they're canceling out, right? So even if it's, multiplied by a factor of 1,000, it doesn't matter because they will cancel each other out. The spot that it does matter is when you get up to the mass per volume. Those have to be grams and mils. So that's why I just get myself in the habit of converting everything to grams and milliliters. That way I'm not going to make a mistake when I do get to the mass per volume. You don't want to give something in grams per liter or milligrams per milliliter. You want it grams per milliliter is kind of standard. So I've just gotten myself in that habit, but that's just so that I don't make mistakes. If you want to save yourself that step, that's totally fine. So we've got pewter, and it is made up of 85% tin. Almost said 25. Don't need that decimal there. 85% tin. And 7% copper, 6% bismuth, and 2% antimony. We want to figure out the amount of tin and copper that are actually in that 150 kilogram statue. So I'm looking at tin and copper, right? Cu. And also the other thing that I know is the mass of the solution. So you're going to see me convert it to grams just because it makes me feel better. To go from kilograms to gram, we have to multiply by 1,000. Okay, so basically we have to figure out what the mass is for tin. It's going to be 85% of the 150,000 gram statue, and then copper is going to be 7% of that. We're going to show all of those steps so it's really clear. I'm going to make this bigger so I've got a little bit more space, so bear with me. Sorry, this one has a hard time staying straight. There we go. Okay, so for tin, I want mass to mass percent, and it is going to be equal to mass of the solute over mass of solution times 100. What do I actually want though, I want the mass of the solute, which is tin. Sorry, I'm going to give myself a little bit more space. Scratch that out. Move it over to the left. I want the mass of the solute. So that's going to be mass per mass percent times mass of solution. Which is 85%. And remember, if we don't have a percent button on our calculator, you should be typing in 0.85 into your calculator. And it's times, multiplied, stop that, there we go, by the total mass of the solution, which is the entire statue. I'm getting 127,500 grams. And then you do the exact same thing for the copper. How is that? Is that okay for everybody? Questions, concerns? Nobody's emotionally distressed over that? Well, that's good. I do the same thing for the copper. And I'm just going to go, because I've already rearranged it, look at, I've got this beautiful, look at, it's rearranged. Mass of the solute equals mass per mass percent times mass solution. That's all rearranged. I'm not going to write that again, especially if it's on a test or an exam and I'm in a time crunch, right? So I'm actually going to go straight to the mass of the solute, which in this case is the mass of the copper, and say that it is 7% or 0.07 times, wow, did not leave myself enough space. $150,000 grams. So just for those of us who need to see that, that's 0.07 times 150 000 10,500 grams of copper. So far, so good. That's a good practical application too. I like how it had, the statue is actually the solution. Because sometimes we think of solutions that they've got to be liquid and dissolve nicely. And it's nice that you can see it that way. You can treat the whole object as the solution because they were all mixed together. They're just in solid form. Next up, volume to volume percent. So this is just like what we just did with the mass to mass. It's essentially just like what we just did with the mass to volume, except we've got, they've got to be both volumes. And again, if these were both liters, they would totally cancel each other out, and that's totally legit. Just remember that in the mass to volume formula, you have to be in milliliters. So if you want to get in that practice of converting to milliliters, it's probably a good idea. So we're going to determine the volume to volume percent if 50 milliliters of rubbing alcohol is added to 250 mils of water. Okay, well, what's what here? That's the tricky part. Now we're into volumes. We've got 50 mils of rubbing alcohol added to 250 milliliters of water. What's what? I need, in order to do this question, I need the volume of the solute divided by the volume of the solution. The solution, come on, there you go. Solution is made up of the solute plus the solvent. Which one's which? In this case, is rubbing alcohol the solute or the solvent? What do you think? That's usually a good indicator, right? Solute, so yeah, absolutely. The water, like we talked about, was it yesterday or the day before? The day before. Water is often a really good solvent, right? It's a polar solvent and dissolves a lot of stuff. We've got rubbing alcohol here, so that's to definitely have an alcohol group on it. And it is going to easily dissolve in to the polar solvent of water. So we know that our solute is the rubbing alcohol. And the solvent then must be the water. So to get the volume to volume percent, I need volume of solute over volume of solution. Almost said solvent, but it's not. It's over the solution. Okay. So volume of solute, what have I got? Okay, I said my solute, shrink this down a bit here. My solute, there it is the rubbing alcohol. Okay, so 50 milliliters. I can put that in. There we go. 50 mils. Yes. Volume of solution. Oh, yeah, you want me to put the 100? Thanks, Maria. Good catch. Where's my eraser? Come on. There it is. Did I say 500 too? This always happens once you move it around. I said 50? Or I just wrote down the volume? Okay, we'll just scratch it. Sorry, gang. 50 milliliters of solute. All right, now I'm back on track.
Isn't that a ratio?
Yeah, but it didn't work that time. Okay, now what's my volume of solution? Maria says 300. I think that that's probably a good idea. Why? Because the solution is the solute and the solvent. So I'm going to say volume of the solution is going to be 300 mils. Yeah, 500 over 300 would not have worked, all right? Is that okay for everybody? You had to add those two together because that's the total solution. So you have to think about that for a sec and add them together. Because the volume is actually, when you don't have something, when you're not adding a solid, it actually, if you're adding a liquid into a solution, it increases the total volume of the entire thing, right? It's a little bit different with a solid because it can dissolve into it so nicely. So we should get, what is that, 16.7%? 5 divided by 30, yeah. What do we think? So far, so good? Sweet. Oh, here's the parts per million and parts per billion. ppm and ppb. Hey, you've probably seen that before. You've probably seen this written on certain types of chemicals that even actually can be found in the house. It's a really great way, especially just to kind of reach out to the general public who might not have the idea of any of the normal prefixes that we use in science. They don't really understand that, but parts per million and parts per billion, million and billion are numbers that they actually really get, right? So what we're going to do is anytime we've got a 10 to the negative 6 situation happening, we're going to say that that is parts per million. And then if it's 10 to the negative 9, right there, we're going to say that's parts per billion. Okay? So it's just kind of like replacing that 10 to the 6 or 10 to the 9 and make sure we have an understanding of what that actually means. So where does it come from? To express a concentration in the form of parts per million or parts per billion, we're going to use the following. To get parts per million, you need the mass of the solute, just like before, over the mass of the solution, which you need a gram sign there, right? Sorry, gang, that wasn't there. And then you got to multiply that by 10 to the 6. And we know that 10 to the 6 is basically a 1 with 6 zeros. Let's try and write that nicely.
Angela Simpson to the main office, please. Angela Simpson to the main office.
Huh, weird. Just like a 10 to the 9 is a 1 with 9 zeros. Do, 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 do. Ooh, just barely got those in there. Another way you can look at it is to take whatever quantity that you're given. Oh man, stop that. Of the solute, put that over top of 10 to the 6 grams of solution. It's essentially the same thing. That'll make sure that it actually gets into the parts per million or parts per billion format. Okay, so some of the homework that you're doing is just kind of practicing this stuff, making sure that if you get those numbers, you're going to convert it. If you get times 10, you have to multiply them through by times 10 to the 6 or times 10 to the 9. They can actually replace those with parts per million and parts per billion. Let's try that. Let's try doing a version of that. Ooh, mercury poisoning. Yeah, that's an issue, eh? This is actually mercury. There's a fair amount of mercury actually found in fish, and that's why we, in Canada especially, we recommend that you're not eating fish more than 2 times a week, 2 to 3 kind of maximum. So probably if you're over 3, you're in that really danger zone because there's a fair amount of mercury that is in the lakes and oceans and can actually really bioaccumulates in fish. Ooh, you remember that term from grade 9 science? Yes, we bust out some ecology there. So yeah, bioaccumulates in fish, and that means that you can't get rid of it. Like their body just won't purge it out. Your body doesn't either, right? Like when you eat mercury, your kidneys and liver don't filter this stuff. It ends up causing really big plaques, and sometimes these heavy metals can actually cause plaques in the brain. Good example. I don't know if I've ever told you this one. I feel like I tell it a lot, so if I repeat the story, you just go with it and pretend that it's brand new information. So the Roman Empire, way back when, like, they had huge dominance of that kind of Mediterranean area for such a long time. The historians actually think that the Roman Empire was brought down by a couple of key emperors that made some pretty bad decisions. And there's good evidence to suggest that part of it was because of lead poisoning in the brain. And the Romans used to make their amphora. The amphora are wine jugs. They used to make their wine jugs out of lead. Who wants to lift that? Like, that's just crazy, right? So, but they would pour their alcohol into these wine jugs, and the alcohol would cause the lead in the wine jugs to leach out into the wine. So they'd be drinking heavy lead, essentially. And what that does, lead in your body will actually build up and form these crazy thick plaques in your brain because you can't get it out. And if you're getting plaques in your brain, it's kind of the same theory that we think is actually behind Alzheimer's disease, that there's a possibility that plaques are forming in the brain, and that actually interferes with the connections that are being made in the neurons in the brain. So it actually interferes with the ability to make good decisions. It depends where the plaques are located, but specifically there were two emperors that were kind of back to back that kind of showed evidence of going completely nutso and crazy. And it's postulated that a good reason of it is because, they like to drink their wine so much, and insisted that the Romans loved to use, they scavenged a lot of beautiful marble and heavy metals from other civilizations and other pieces of art and stuff like that. They love they're really materialistic that way. They love that kind of stuff, and easily it's over extravagant to make a jug out of lead, especially in Roman times, right? So, but that could have been the downfall, that there's a lot of people in ancient Rome walking around with a little bit of lead poisoning, making them become a little crazy. And if you hear some of the stories of what Roman life was actually like for these richer people that were living in that time, they did some crazy stuff. Like, they did some totally crazy stuff. And come on, like, watching people fight to the death in a Colosseum is just completely nuts. Letting animals fight humans in a Colosseum is completely nuts. And maybe that's why. Maybe because there is actually a really good, less savage reason. Maybe it's because they actually had heavy metal poisoning. Who knows? Anyways, that was totally sidetracked. I should have pressed stop on that one. Now they get to hear myself. Oops. Oh, well. You get to hear that big blurb. Oh, well. Moving on. Anyways, don't get mercury poisoning or lead poisoning is the moral of the story. Okay, so symptoms of mercury poisoning actually can become apparent in a person if you've got an accumulation of more than 20 milligrams of mercury in their body. We're going to see if we can express this as the amount as parts per million for a 60 kilogram person. And then we're going to express it as an amount of parts per billion. And then we're going to express it as a mass to mass percent. All right? Ready? Okay. I think in grade 9, you should have spent some time actually looking at all of the metric prefixes, where we start with remember this chart where we start with the gram in the middle? And then we've got decimeter, centimeter, millimeter, a couple other spots. And then there's the micro spot. And you can go the other direction too. This is deca, hecta. There's your kilo. Oh, there it is. And then bam, bam, 2 other things. And then there's mega. That's the 10 to the 6. And that was the 10 to the negative 6 off of the base unit, where our base is a gram, a liter, a meter, a second. If that seems like something that's a little obscure and that you would like more information on that, I have I can pull it out of my physics book. I have an awesome kind of staircase that really helps you get the right spots. If you need help converting from one spot to the next, for those of you who need it, just let me know. All right, so let's see what we've got here. We've got mass of the solute and it's 20 milligrams. So right away, what do I want to do with that milligram? I'm going to convert that to grams. So I've got milla, and I got to go 1, 2, 3 spots. So that means I'm moving the decimal 3 spots to the left. Just like I had to go left here, I'm going to go left here. So let's do that. I should get 0.02 grams. The mass of the solution. What's the solution in this situation? The 60 kilogram person. Perfect. That's a tiny person. You multiply that by 2.2. 130 something. Yeah. So this is in kilograms. So for those of us who need a little bit of support here, the kilogram, we want to go from the kilogram to the gram. So we're going to go 1, 2, 3. 3 spots over to the right. I'm essentially adding 3 zeros, right? 60, 1, 2, 3. Because our decimal place would have been there, right? So I would want to go 3 to the right. So now I'm going to go 3 to the right. Nice. How much space do I have? Not much. I'm going to go sideways now. Sorry, does that mess you up too much if I do that? Stay with me. It's going to be okay. Okay, so parts per million. So if we want parts per million, we're going to look up to the formula up above, and it actually says the mass of solute over mass solution and times 10 to the 6. Oops. I almost wrote 20. Aha. That would be bad form. Bad form. So when we do 0.02 divided by 60,000 on your calculator, what do you get?
There's like 6 zeros before the first 3.
So, yeah. So you did, so if we like were able to, if this was gone here, you would have got, did you put the 10 to the 6 in?
Yeah.
You did put the 10. Okay, never mind. Scratch that. He put the 10 to the 6 in. Okay, so when we, if you put the 10 to the 6 in, then you're actually going to get, it does this, right? You said 6. 1, 2, 3. Like that?
Yeah.
2, 3, 4, 5. Yeah. Okay, so what you're essentially doing there is you want to replace that, these, all those zeros right there, with a nice ppm. So this is going to become this. Parts per million. Can I borrow your calculator for a second? So when you, your answer should give you, when you do 0.02 divided by 60,000, it should give you all of those zeros in front of that 333. And then essentially that 10 to the 6, what that 10 to the 6 is doing is getting rid of those zeros. So it's bringing, and you want to show that you blah, 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 blah. You want to acknowledge that you've done that. That 10 to the 6 actually is significant because it is the parts per million, so you want to make sure you write down the parts per million. Does that make sense? I don't feel like I explained that very well. Okay, so when you punch this in on your calculator, you should get, if you do all of this in one step, you should get this answer. Okay, If you just did this, you'll get this. And then you need to do the times 10 to the 6th. Does that make more sense? But that the 10 to the 6 is replaced with the ppm. Hey, could you go to parts per billion right from there? Yeah, we could do that. What would you just have to multiply that by 1,000 to get there. It should be 333 parts per billion. But let's say we didn't have to find the parts per million first. We can actually show our steps for those of us who would appreciate that. The parts per billion, whoops. Parts per billion would be 0.02 grams over 60,000 grams times 10 to the 9, and that will give you 333 parts per billion. How's that? Does that feel okay? I feel like I kind of messed that up a little bit. Does that seem clear? Alrighty. The last thing that we need to do there is express that amount as a mass, what is it? Mass per mass percent? So we'll find some space here and say mass to mass percent is going to be mass of the solute over mass of solution . 0.02 grams over 3 grams times 100, and we should get, oh my goodness, how many zeros are there? Just 3, I think. Oh, it's 4. So that's a tiny amount, when you look at it as a percent. Isn't that crazy that symptoms of mercurial poisoning, that's all you need, is that's a tiny, tiny percent. Makes me feel like I did it wrong, but no, it's right. It's a tiny percent of amount of mercury that you need before you start to feel the effects. It's not good. It's a small percentage. Wow, that took way longer than I thought. Oh, it's because I told that crazy story. Okay, so the rest of the time that you've got, you can work on doing those questions in your textbook. And tomorrow we have a shorter lesson, but get you a lab activity. That'll be kind of nice. Sound good?